Welcome to this rigorous scientific lecture on detecting new particle signals at colliders. Today we'll walk through the complete workflow that physicists use to claim discovery of a new particle, from detector calibration all the way to final validation. The fundamental challenge in particle physics is distinguishing a genuine new particle signal from background processes. Let me explain what this means. The signal is the rare new physics event we're searching for, perhaps a Higgs boson, or a supersymmetric particle, or something completely unexpected. The background consists of known standard model processes that can mimic our signal. These are well-understood physics processes that happen much more frequently than our signal. Imagine you have thousands of background events, and maybe only 10 signal events. It's like finding a needle in a haystack. This is why rigorous background modeling is absolutely critical. Step 1 in our workflow is detector calibration. Before we can search for anything, we must ensure our detector is measuring particle properties accurately. Why does calibration matter? Because systematic uncertainties in our detector response can easily create fake signals or hide real ones. Let's take a concrete example. We calibrate our energy scale using the Z-boson, which has a precisely known mass of 91.2 giga-electron-volts. The Z-boson mass is 91.2 giga-electron-volts. This is measured to exquisite precision from previous experiments. We collect thousands of Z-boson decays to electron-positron pairs or muon-antimuon pairs. These are clean, easy-to-identify events. We plot the invariant mass of electron-positron pairs. We should see a sharp peak at 91.2 giga-electron-volts. If the peak appears at 90 or 92 giga-electron-volts, we know our energy scale is wrong. We calculate a correction factor, true Z-mass divided by measured Z-mass. This factor is then applied to all energy measurements in our detector. After calibration, typical energy scale uncertainties are 0.1 to 1%. This might sound small, but it matters enormously when searching for new particles. We also calibrate momentum measurements, timing systems, and particle identification algorithms. Each subsystem requires dedicated calibration procedures. Step 2 is defining control regions. Control regions are carefully chosen parts of our data where we know the signal should be absent, but background is present. The purpose of control regions is to validate our background model. If we can accurately predict the data in control regions, we gain confidence in our background predictions in the signal region. Let's say we're searching for a new particle that decays to 2 photons with an invariant mass around 125 giga-electron-volts. This is exactly how the Higgs boson was discovered. We define control regions on either side of our signal region. For example, 100 to 110 giga-electron-volts and 140 to 150 giga-electron-volts. We use these regions to validate our background predictions. A key principle is that control regions must be kinematically similar to the signal region. They should have the same detector acceptance, same trigger requirements, and same background composition. You might ask, why not just use Monte Carlo simulation for the background? Why do we need control regions? The answer is that simulations have uncertainties. Parton distribution functions, higher order corrections, and detector modeling all introduce uncertainties. Data-driven methods using control regions are more reliable. Step 3 is fitting background models. We use the control regions to fit a smooth, functional form that describes the background shape. A common approach is to use a smooth polynomial or exponential function. The key is that the function should not have artificial bumps or features that could create fake signals. For example, the background might be modeled as b of m equals p0 times exponential of negative p, 1 times m minus p2 times m squared, where m is the invariant mass. We fit this function to the data in our control regions. The fit determines the parameters p0, p1, and p2. We perform a chi-squared goodness of fit test. If chi-squared divided by degrees of freedom is close to 1, our model describes the data well. Chi-squared per number of degrees of freedom approximately equals 1 indicates a good fit. Much larger than 1 suggests our model is inadequate. Let's do a back-of-the-envelope calculation. Suppose in our signal region we expect about 1,000 background events based on our fit. The statistical uncertainty is roughly the square root of 1,000, which is about 30 events, so we expect 1,000 plus or minus 30 background events. Systematic uncertainties from the fit procedure, energy scale, and luminosity might add another 3 to 5% or 30 to 50 events. So our total prediction becomes 1,000 plus or minus 30 statistical, plus or minus 40 systematic. Understanding these uncertainties is crucial. Step 4 is looking for residual peaks. After subtracting our background model, we look for localized excesses that could indicate a new particle. We plot data minus background prediction versus invariant mass. In the absence of new physics, this should fluctuate randomly around 0. If we see a localized peak, like this excess at 125 giga-electron volts, that's interesting. But we must be very careful before claiming discovery. We must account for the look elsewhere effect, also called the trials factor. If we search over many mass ranges, we increase the probability of finding a random fluctuation. We distinguish between local significance and global significance. Local significance asks, what's the probability of a fluctuation at this specific mass? Global significance asks, what's the probability anywhere in our search range? The standard discovery threshold in particle physics is 5 sigma. This corresponds to a p-value of 2.87 times 10 to the negative 7, or roughly a 1 in 3.5 million chance. Why 5 sigma? Because history has taught us that lower thresholds led to false discoveries. The pentaquark in the 1990s, the 750 giga-electron volt diphoton excess at LHC, both disappeared with more data. A simple estimate of significance is S divided by the square root of B, where S is the number of signal events and B is background. This assumes Poisson statistics. For example, if we have 1,000 background events, we need about 25 times the square root of 1,000, which is roughly 160 signal events for 5 sigma significance. Actually, more careful calculations give about 125 signal events for 5 sigma. Step 5 is blind analysis. This is a crucial technique to avoid experimenter bias. The principle is simple but powerful. Don't look at the data in the signal region until your entire analysis procedure is finalized and documented. Why do we blind? Because human psychology is tricky. If you see an excess, you might unconsciously adjust your cuts or background model to make it more significant. If you see nothing, you might keep tweaking until something appears. During a blind analysis, the signal region is literally hidden from analyzers. You can only see the control regions. You validate your method there, and only when everything is ready do you unblind. Unblinding is often a formal ceremony. You document your analysis procedure, get it reviewed by collaboration members, and then collectively open the box to see what's inside. You might ask, what if we see nothing after unblinding? Isn't that a waste of effort? Not at all. Null results are valuable science. We set limits on new physics models, constrain theoretical parameters, and guide future searches. Science is about finding the truth, not confirming our hopes. Step 6 is validation with independent channels. If we see a signal in one decay mode, we should see it in other decay modes predicted by theory. Let's use the Higgs boson as an example. The Higgs can decay to multiple final states: 2 photons, 4 leptons, 2 W bosons, 2 Z-bosons, 2 B quarks, 2 tau leptons. Each decay channel has different branching ratios, different backgrounds, and different experimental signatures. They are statistically independent probes of the same particle. The crucial consistency check is, do all channels see an excess at the same mass? If the diphoton channel sees something at 125 giga-electron volts, but the ZZ channel sees nothing, we'd be suspicious. For the Higgs, the diphoton channel measured a mass of 125.4 plus or minus 0.4 giga-electron volts. The ZZ to 4 lepton channel measured 125.1 plus or minus 0.3 giga-electron volts. These are beautifully consistent. When we combine all channels, we get a Higgs mass of 125.09 plus or minus 0.24 giga-electron volts. The agreement across channels is strong evidence for a real particle. We also check branching ratios. Theory predicts the relative rates for different decay modes, If we see too many diphoton events compared to ZZ events, something might be wrong. Step 7. The final validation is confirming that the signal scales with energy and luminosity as predicted by theory. This is the smoking gun that you've discovered real physics. The signal rate should scale linearly with integrated luminosity. If we double the amount of data collected, we should see twice as many signal events. Number of signal events is proportional to the integral of luminosity over time. This is just counting statistics. More collisions means more signal events. But background also scales with luminosity. So why is this a test? Because systematic effects or detector artifacts might not scale properly. We plot signal events versus integrated luminosity. If we see perfect linear scaling, that's very reassuring. A detector artifact or analysis mistake would likely show nonlinear behavior. We also check energy scaling. The production cross-section for a particle depends on the center of mass energy in a predictable way from theory. For example, the Higgs production cross-section from proton-proton collisions varies with the square root of s, the center of mass energy. The LHC has run at 7 tera-electron volts, 8 tera-electron volts, 13 tera-electron volts, and 13.6 tera-electron volts. We can compare signal rates at these different energies. Theory provides precise predictions from quantum chromodynamics calculations. Gluon fusion, vector boson fusion, and associated production each scale differently with energy. For Higgs production via gluon fusion, the ratio of cross-sections at 13 tera-electron volts to 8 tera-electron volts is approximately 2.3. This is a firm prediction we can test. When we measure this ratio experimentally and compare to theory, we test not just that the Higgs exists, but that we understand its production mechanism correctly. Let's do another back-of-the-envelope calculation. Suppose we need 5 sigma significance. How much luminosity do we need? A rough formula is required luminosity equals 25 divided by cross-section times efficiency times branching ratio. The 25 comes from needing 5 sigma, which is 25 squared over background. For Higgs to diphoton at 8 tera-electron volts, cross-section is about 20 picobarns, efficiency may be 0.3, branching ratio 0.002. This gives roughly 2 times 10 to the 15 per centimeter squared, or about 20 inverse femtobarns. This is the order of magnitude needed, and indeed the Higgs was discovered with about 25 inverse femtobarns. Let's put this all together with the real-world example of the Higgs boson discovery. In 2011, both ATLAS and CMS experiments saw hints of an excess around 125 giga-electron volts. But it was only 3 sigma. Interesting, but not significant enough to claim discovery. In 2012, both experiments collected more data through the first half of the year. They performed rigorous blind analyses, finalizing all procedures before looking at the signal region. On July 4, 2012, both experiments unblinded their analyses. Both saw clear excesses at 125 giga-electron volts with over 5 sigma significance. The discovery was announced at CERN to worldwide excitement. ATLAS reported 5.9 sigma significance. CMS reported 5.0 sigma. 2 independent experiments with different detectors, different analysis techniques, both seeing the same thing. This is gold standard evidence. From 2012 to 2015, both experiments validated the particle's properties. They confirmed signals in multiple decay channels, measured the mass precisely, and checked that production rates matched standard model predictions. The particle had the right mass around 125 giga-electron volts, spin 0 as predicted, and couplings to other particles proportional to their masses. All properties consistent with the standard model Higgs boson. In 2013, the Nobel Prize in Physics was awarded to Peter Higgs and François Englert for the theoretical prediction made almost 50 years earlier. This validated both the theory and the experimental discovery. Let me talk about systematic uncertainties, because this is where discovery claims can fall apart. Major sources of systematic uncertainty include luminosity determination, energy scale calibration, Parton distribution functions, and higher-order corrections in theory. Luminosity uncertainty is typically 2 to 5%. This affects both signal and background, but it matters for cross-section measurements and comparisons to theory. Parton distribution function uncertainties affect how we predict signal rates. Different PDF sets can give 5 to 10% variations in predicted cross-sections. For channels involving jets, jet energy scale is often one of the largest systematic uncertainties. It can be 3 to 5% and affects background estimates significantly. An important question: how do we properly combine statistical and systematic uncertainties? For independent uncertainties, we add them in quadrature. Total uncertainty squared equals statistical uncertainty squared plus systematic uncertainty squared. But here's the key difference. Statistical uncertainties shrink as 1 over square root of n with more data, but systematic uncertainties typically don't shrink. This is why controlling systematics is crucial. Modern analyses increasingly use machine learning to improve signal detection, though the fundamental workflow remains the same. Neural networks can be trained to discriminate signal from background using many kinematic variables simultaneously. This can improve sensitivity compared to simple cuts. But even with machine learning, we must still validate on independent control samples. The neural network might learn spurious correlations or detector artifacts. Interpretability is crucial. We can't blindly trust a black box algorithm. We need to understand what features the network is using and verify they're physically meaningful. Machine learning is a powerful tool, but it's not a replacement for physics understanding. You still need the full rigorous workflow: calibration, control regions, blind analysis, and multi-channel validation. Let me emphasize the importance of reproducibility in modern particle physics. All analysis code should be version-controlled, documented, and ideally publicly available. This allows other physicists to reproduce your results. CERN has pioneered open data initiatives. After a few years, collision data is made publicly available so anyone can reanalyze it. When independent groups reanalyze the same data with different techniques and reach the same conclusions, this dramatically strengthens confidence in the results. Scientific publications must include detailed methodology, all systematic uncertainties, and enough information for others to reproduce the analysis. Looking forward, particle physics faces exciting challenges in signal detection. The high-luminosity LHC will provide 10 times more data by 2040. This enables searches for even rarer processes, but also creates challenges with increased backgrounds and detector occupancy. We'll need even better background modeling techniques to find subtle signals in this sea of data. Data-driven methods will become increasingly important. Quantum computing might revolutionize signal processing and pattern recognition in high-energy physics, though practical applications are still years away. Multi-messenger astronomy, combining gravitational waves, neutrinos, and electromagnetic signals, opens new discovery channels that weren't possible before. Let me summarize the 7-step workflow for detecting new particles. Step 1. Detector calibration using well-known particles like the Z-boson to ensure accurate measurements. Step 2. Define control regions to validate your background model in signal-free areas. Step 3. Fit smooth background models using data from control regions. Step 4. Look for localized excesses or residual peaks after subtracting the background model. Step 5. Employ blind analysis techniques to avoid unconscious experimenter bias. Step 6. Validate any signal candidate in multiple independent decay channels. Step 7. Confirm that the signal scales correctly with energy and luminosity as predicted by theory. Why does this rigorous workflow matter so much? Because history shows many false discoveries that resulted from inadequate procedures. The supersymmetric particle hints that disappeared. The faster-than-light neutrinos that were a cable error. The 5 sigma standard, combined with multi-channel validation and proper systematic uncertainty treatment, prevents premature discovery claims. Public trust in science depends on rigorous, reproducible methodology. When we claim to discover a new fundamental particle, we must be absolutely certain. This workflow protects against both random statistical fluctuations and systematic experimental errors. It's the product of decades of hard-learned lessons. Let me close with some final thoughts about science as a process. Discovery is not a single eureka moment. It's a gradual process of accumulating evidence, checking and rechecking, validating with independent methods. Collaboration is essential. Atlas and CMS each have thousands of physicists. Every analysis is reviewed by dozens of experts before publication. Remember that negative results advance science too. If we search for supersymmetry and don't find it, we've learned something important about nature and constrained theoretical models. The next great discovery might be waiting in data that's already been collected, or it might require future colliders operating at higher energies. The search continues. Thank you for joining this rigorous scientific journey through the methodology of particle detection at colliders. Remember, discovery requires not just sophisticated detectors, but sophisticated analysis procedures that eliminate bias and quantify uncertainties at every step.